Today, I want to share with you some lessons that I've been fleshing out with my team at Landing AI about how to move from model-centric to data-centric AI and the implications on systems. I hope these ideas will be helpful to you in your work. If you'd like to learn more about data-centric AI, I'd recommend watching Andrew Ng's talk on MLOps, where he explores the concept of data-centric AI in more detail. We've seen that AI systems are essentially code plus data. The code meaning the model or the algorithm, and the data that that model is trained on. About a year ago, the team at Landing AI was working on detecting defects in steel sheets, like those pictured here. You can imagine large rolls of steel that have scratches, notches, foreign material, water stains, or oil stains. In this case, an AI system is designed to look at images captured of those steel sheets and identify these defects. The team started from a baseline system that had accuracy of 76%, and the target requirement was 90%. I remember in December of 2020, the team flew out to visit on site, and there were multiple teams that were competing to develop a solution that could solve this problem. Some of the teams took a model-centric approach. We actually took a data-centric approach. Which one do you think was more effective? So it turns out in this case, the data-centric approach was more effective. We've seen this pattern repeated over other visual inspection problems, including solar panels and surface inspection. In the case of steel defects, the data-centric approach was able to boost accuracy by almost 17%, whereas editing the model improved accuracy by 0%. Upon digging deeper into the data set, we realized that some classes of defects were underrepresented and some were mislabeled. Fixing those errors led to the improvement in accuracy. Now that you have a better idea of what data-centric AI is, let's look at the implications on computer systems. We know that deep learning has created enormous computational demands. Larger models trained on larger datasets have led to much more accurate machine learning systems. The largest of models, like language models like GPT-3, require large training clusters with thousands of computers working together to train a single model. Looking ahead, using scaling laws, we can project that the computational requirements, the model sizes especially, but also the data sizes, and therefore the computational requirements are going to increase substantially. But this is a model-centric view. Switching to a data-centric view changes the perspective. Next, I want to share with you a lesson learned from the theory of machine learning. A little while ago, I asked Leslie Valiant if he could explain the scaling laws that we observed in very large neural networks. And he pointed me at this relatively old idea developed by one of his students, Michael Kearns. There are two ways of improving accuracy: small data and big data. I want to illustrate this with an example. Imagine that you have a small amount of data and it's relatively noisy. It has noisy labels. So imagine I'm plotting voltage against speed. And if you see the red X's here, they represent observations or data. And as you can see, there are many possible functions that could be reasonably good fits for this data. But because the data is so noisy, it's hard to know which one is a better fit. Having more samples allows averaging out the noise. You can draw confidently the relationship between voltage and speed. An alternate approach is to use small data. If all of the observations have very little noise, then it's very straightforward to fit a curve and be confident that that is actually the true relationship. So let's contrast these two viewpoints and their implications on systems. The model-centric view can train bigger models on more data, and that leads us to building faster, larger scale training systems that can handle all of that data and the large models that are required to fit that data. However, using a data-centric view, you can train smaller models on less data, making the computational problem a lot simpler. This reduces the computational requirements of both training and inference. Smaller models on less data are cheaper to train, and smaller models are cheaper to deploy. Now that we haven't used all of our resources on training or inference, we have additional computational resources left over that we can use to help us clean our data. I remember in the early days when deep learning was just starting to take off, machine learning researchers would often trade models in MATLAB. We didn't have frameworks at the time. Similarly, we would train our models on laptops. We didn't have powerful training clusters with dedicated training or inference accelerators. We don't have similarly advanced systems or computational technology to clean data and improve data. I've seen many machine learning teams use a file system to store their data and the file browser to sort through it and label it. At Landing AI, we built a new tool called Landing Lens that allows us to systematically clean, create, and improve datasets. Take a look at this video explaining how it works.
Hello, my name is Whit Blodgett. I'm the product manager for Landing Lens here at Landing AI, and I'm going to give you a quick walkthrough of our platform. People are often surprised when you tell them that full AI solutions are only about 5 to 10% AI code. Majority of the solution includes ancillary tasks such as data management, labeling, augmentation, error analysis, iteration, and edge device management. Landing Lens approaches this with a combination of 3 modules that enable your team to successfully train and deploy AI models that perform human-level visual inspection tasks at scale on the edge. First, we'll talk about data management. Building AI for defect detection is challenging in itself because you generally don't have too many examples of defects to label and train your models on. As such, it's critical your team makes the best use of limited image collection. Data management includes a variety of tools and features that help your team align on what qualifies as a defect and what does not, as well as a way for you to actually test how well their labels align with each other. Here, your team will work iteratively to build a defect book that will help future labelers consistently identify defects. Next, armed with this defect book, your labelers will label images with either bounding box or segmentation labels. Finally, once these datasets have been labeled, reviewed, and approved, you'll export them into our next module, model iteration. Model iteration is all about giving you the flexibility of a professional machine learning engineer while removing all the complexity of training models with open source code, Jupyter notebooks, and custom environments. We take care of all of that and instead provide you a codeless UI, so whether you're a PhD in machine learning or a technically skilled person, you can easily train models and test performance before deployment. Features in this module include codeless model training, where you can specify various hyperparameters such as learning rate, epoch count, and data augmentation. This model also includes auto model tuning in the background and a training page where you can see live training progress, including performance curves and things like that. Once trained and validated, we offer in-depth performance metrics to help you understand where your model is strong and where it needs work. Things like precision, recall, mean IOU. Finally, and probably most importantly, we offer an in-depth error analysis tool where you can compare labeled images to predictions made by the model. Once you've reached a performance level that serves your purpose, generally beating human level performance, you send your model to the next section, deployment. Deployment is where the rubber meets the road. It enables you to quickly deploy models in your production environment. In particular, we provide features such as one-button deployment on edge or virtual devices, device fleet management, environmental checking and change detection, and monitoring dashboards, as well as data flow that integrates with the rest of the platform, so you can retrain models on newly captured data that your model might not recognize initially. Regardless of the hardware you use, our platform integrates seamlessly with devices, PLCs, and cloud environments. These tools combined enable your team to deploy and manage an infinite number of AI edge devices. For now, we'll stop here. Thank you so much for your time and have a great day.
Let's look at a specific example. How can a technology help us clean data? This is the error analysis page in Landing Lens. It allows you to visualize the predictions being made by the model and see where it's making mistakes. In the first image, the system correctly identifies a crack as a defect. In the second image, it misses it. I'd like to understand why. Using image search technology, we can find the defect that was missed automatically and find the related similar training images in our training dataset that was used to train the model. Once we've found those images, we can inspect their labels to make sure that they're labeled appropriately. After making changes to the dataset, we can retrain our model and observe whether the model is now able to identify this type of defect. A capability like this requires not just model training and inference, but also the ability to search back into a large, unlabeled, potentially unlabeled data set. To make this cycle as efficient as possible, training, inference, search, and front-end steps should be as fast as possible. Today, there's a long way to go, and they're not nearly interactive. Many components here are batch jobs. Imagine running a training job as one of the steps here and waiting for it to complete. This is one example of a new systems problem exposed by a data-centric approach. We recently organized a data-centric competition where the submissions were encouraged to improve the dataset, not just improving the model. We found that many of the top submissions invented advanced technologies like those that I just mentioned. One submission started with an initial seed dataset, augmented it using a data synthesis pipeline, and then searched through it to find similar examples using an image search algorithm that I just mentioned. Migration from model-centric AI to data-centric AI is just getting started. If you're interested in participating, I'd encourage you to attend the NeurIPS workshop on data-centric AI.